This is going to be over section 23.6. We're going to be looking at the nature of light. Light, of course, is an electromagnetic wave. When emitted or absorbed, it also shows particle properties. That's fun. Light is emitted by accelerated electric charges that have been given excess energy by heat or electrical discharge. The speed of light is a fundamental physical constant. A wavefront is a surface of constant phase. Wavefronts move with a speed equal to the propagation speed of the wave. A ray is a line along the direction of propagation perpendicular to the wavefronts. So there's, we're going to start looking at optics from this point forward. We're going to take a look at some of the foundation that's needed, and we're going to look at some of the developments like optical fibers, holograms, optical computers, and things of that sort. We're going to take a look at the various possible descriptions of light. In other words, is it a wave? Is it a particle? And what do those implications mean? Until the time of Isaac Newton, most scientists thought that light consisted of streams of particles called corpuscles emitted by visible objects. Galileo and others tried unsuccessfully to measure the speed of light. So around 1665, evidence of wave properties began to emerge, and by the early 19th century, evidence that light is a wave had grown very persuasive. The picture of light as an electromagnetic wave isn't the whole story. Several effects associated with the emission and propagation of light revealed that it also had a particle aspect. And that is because the energy carried by light waves is packaged by discrete bundles called photons or quanta. These apparently contradict wave and particle properties that had been reconciled since 1930 with the development of quantum electrodynamics, a comprehensive theory that includes both wave and particle properties. The propagation of light is best described by a wave model, but understanding emission and absorption by atoms and nuclei requires a particle approach. So that's fun. The fundamental sources of all electromagnetic radiation are electric charges in accelerated motion. All objects emit electromagnetic radiation as a result of thermal motion of their molecules. This radiation, called thermal radiation, is a mixture of different wavelengths. At sufficiently high temperatures, all matter emits enough visible light to be self-luminous. A very hot body appears red hot or even white hot. Thus, hot matter in any form is a source of light. Familiar examples are candle flame, hot coals in a campfire, coils in an electric room heater, incandescent lamp filaments. And light is also produced during electrical discharges through ionized gas. The bluish light of mercury arc lamps, the orange yellow of sodium vapor lamps, and various colors of neon signs are familiar. A variation of the mercury arc lamp is a fluorescent lamp. This light source uses a material called phosphor to convert the ultraviolet radiation from a mercury arc into visible light. This conversion makes fluorescent lamps more efficient than incandescent in converting electric energy into light. So a special light source that has attained prominence is the laser, which can produce a very narrow beam of intense irradiation. High intensity lasers are used to cut steel, fuse high melting point materials, carry out microsurgery, and in other applications. Low intensity lasers are used to transmit information along fiber optic cables, laser printers, and as pointers in public presentations. Significant characteristic of laser light is that it's much more nearly monochromatic or single frequency than light from any other source. Speed of light in a vacuum, of course, is this, which we usually say 3 × 10⁸ meters per second. And 1 meter is defined to be the distance that light travels in a vacuum in this amount of time. The second is defined by the cesium clock, which can measure time intervals with the precision of 1 part in 10 to the 13th power. If future work results in greater precision in measuring the speed of light, the value just cited won't change, but a small adjustment will be made in the definition of the meter. So let's take a look at wavefronts. Wavefront is going to be the locus or position of all adjacent points at which the phase of vibration of the wave is the same. That is, at any instant, all points on the wavefront are of the same part of the cycle of their periodic variation. During wave propagation, the wavefronts all move at the same speed in the direction of the propagation of the wave. In other words, all of these wavefronts are going to represent different positions of the wave at that time, but all of these are moving at the same speed. So, the crest or trough, or the crest or trough, whatever it happens to represent, they're all moving at the same speed. So this is considered to be a point sound source producing spherical sound waves, alternating condensations and expansion of air. Since we're dealing with sound, we have to have a medium of some sort. Here, when wavefronts are spherical, the rays radiate from the center of the sphere. For a light wave, the quantity that corresponds to the displacement of the surface in a water wave, or the pressure in a sound wave, is the electric or magnetic field. So using these particular diagrams, I've already described what's going on. When wavefronts are planar, in other words, got a plane here, a plane here, a plane here, the rays are perpendicular to the wavefronts and parallel to each other, perpendicular to the rays that cut through. It's often convenient to represent a light wave by rays rather than wavefronts. Rays are used to describe light long before its wave nature is firmly established. And in the particle theory of light, rays are the paths of the particles. So a ray is an imaginary line along the direction of travel of the wave. The rays are the radii of the spherical wavefronts. They are straight line perpendiculars, of course, to the wavefronts. When they travel through homogeneous isotropic material, material with the same properties in all regions in all directions, the rays are always straight lines normal to the wavefronts. We'll have opportunities to see the interplay among the ray, wave, and particle descriptions of light. And a branch of optics for which the ray description is adequate is called geometric optics. The branch dealing with wave behavior is going to be called physical optics. And we'll get to those here in the next few chapters.